Hi there, this video is to look at how to integrate a nice geometric shape known as a polar rose, and this is an example of using polar integration. So a lot of the things that you've come across before for integrating, you've just got y as a function of x. Okay, so maybe you've got some function, let's say f of x, and we want to find the area from a to b. Then what we do is we just approximate that area by a bunch of rectangles underneath it, like so. Okay, and so on. And each of these rectangles has an area, so the height of it is just the value of the function. So let's call one of these areas delta A. So it's just the value of the function multiplied by some change in x, delta x. So the total area is just found by summing those together. And if we make delta x small enough, then we replace the summation sign, the sigma, by an integral. So we integrate from a to b the function, and delta x becomes a dx. Okay, now there are some curves which are better expressed in polar coordinates. Okay, in particular if they've got some sort of maybe symmetry around the origin, or they wrap themselves around the origin in some way. So the simple example would be a circle. So let's say I've got an arc like this, and this is some function expressed in polar coordinates. So what I have there is, for polar coordinates, any point on the curve is expressed as a distance r from the origin and an angle theta. So r here is a function of the angle. And let's say I wanted to find between these 2 points, A and B, so these are angles that we're integrating in between. Let's say I wanted to find this area in here. So what do? Well, I know that this curve here, I could split it up into lots of sectors that go back to the origin. So rather than rectangles aren't really appropriate here because it tapers in and thinner at one end, but a sector is a good approximation of that area. And the area of one of those is just going to be equal to a half r squared times the angle, and the angle here, let's call that a small change in theta, so delta theta. So the total area would come from summing that. So I'd have a half r squared delta theta, and again, if I make the angle small enough, then we can replace that by an integral. So we integrate from angle A to angle B of a half r squared, let's put the half outside, half r squared d theta. Okay, so this is the area in polar coordinates. So let's use it now to find the area inside of this shape. So this is a polar rose because it looks a bit like a flower, not necessarily a rose, I suppose, but for different values of inside this argument. So we've got 2 here, we get this shape. If it was a 3 or a 4 or 5, you get more and more shapes. So if you go to some graphing software, and the one I tend to use is Desmos, you can put different values in here and you'll get lots of different shape graphs. So let's say I want to integrate it all the way around from 0 all the way around there to 2 pi. How do I go about doing that? Well, the equation I just had was that the area is half the integral from a to b, so I'm going from 0 to 2 pi of r squared. Well, I know what r is now. R is sine 2 theta, so I've got sine squared 2 theta. That's just r squared, and then d theta. So how do I integrate sine squared? Well, I know that sine squared x is equal to 1/2 of 1 minus cosine of 2x. Okay, this comes from rearranging the double angle formula for cos 2x. And this is the typical way that we integrate sine squared. So in this case, I don't have x, I've got 2 theta, so I'm going to replace x by 2 theta in this whole identity. So I've got 1 minus cos 2 times 2 theta, which is 4 theta. So I substitute that in. So the area becomes 1/2 times another 1/2. So the 1/2 that was outside and then the 1/2 from the identity. So it's a quarter in front now. And then I've got 1 minus cos 4 theta, d theta. And the reason for using that identity is that these things now, 1 and cos 4 theta, are things that I can easily integrate. So I get 1/4 theta minus cosine integrates to sine. So I get sine 4 theta. And then because of the reverse chain rule, I've got to divide by the derivative of 4 theta, which is 4. Like so. And then I just need to put in the limits. So if I substitute 2 pi into the sine bit, I've got sine of 8 pi. Well, I know that sine 0 is 0, and then the sine repeats every 2 pi. So sine 8 pi will also be 0. So what I actually end up with is I get the 2 pi from substituting 2 pi into theta, but every other term that I put ends up being 0. So I just get 1/4 of 2 pi, which is then pi over 2. So I actually get a very simple result in the end. So that's a nice little example of polar integration. If you've got a more complicated function for R, you just substitute it in and then think about all the different integration techniques that you've come across and pick out the appropriate one to help you do that. Okay, that's it for now. Bye.